All right. I think now in this section, we will discuss the Taylor expansion, particularly in context of e to the res x function.
Right, right. So I think in the previous segment, we saw that we used this logic that e to the power x and e to the power r and 1 plus r are approximately the same, right?
Correct.
And the mathematical toolkit that enables us to say that is the Taylor series, right? So if we go to the next slide,
Correct.
uh, we can see what that Taylor expansion is. So this should be something that I think students would perhaps remember, I don't know,
Correct.
fondly or not, from their, I guess, basic calculus courses,
Yeah,
right?
I think again class 11 probably first thing. I mean, sometime
Yeah,
or
I
12,
think
I
people
don't
learn
know.
it in undergraduate actually, right? The first,
Taylor expansion?
yeah, I mean the form in which we have written it here, the full form, right?
Yeah, full form. But at least I think class 12 we've been introduced to some kind of
I think the linear version probably, right?
linear
Fx plus
version.
h is the, but I think the full polynomial version. But I mean, we are
I mean, it
talking about
doesn't
our
matter. I
time,
mean,
right?
yeah,
Right.
exactly.
Maybe now
Exactly.
people are more advanced and they may also see this.
Right, right, right.
But what, just to remind ourselves,
Of
what is the
course.
Taylor expansion telling us? So basically, it's an idea that suppose we have a function, and this is a function which is differentiable, and we want to find the value of the function around some point x naught, right? So this
Correct.
Taylor expansion would be that we can approximate it by a polynomial, right? And
Correct.
you can decide up to which degree of polynomial you can go to, but this is the formula that you see here in the screen. This should hopefully bring
Hmm.
back memories. So several things to note from here, right? That for example, if you put in the value x equal to x naught, the left hand side obviously is f x naught, but the right hand side, this x minus x naught terms all disappear, right? So the only term that is
Correct.
left remaining is this f of x naught, right? So that's why we are
Correct.
saying that this agrees with f at x naught, right? And it also matches its the n derivatives. The information that is there in the n derivatives is there in the nth degree Taylor polynomial, right? The other
Correct.
thing to note is that this approximation gets better and better if we are taking a value of x which is close to x naught, right? Why is that the case? Because in that case, all these terms are pretty much become either very close to zero, right? Remember that x minus x naught is the difference. So if this is small, then most of these terms can be ignored. But if you are taking a point which is very far from x naught, then these terms kind of like become important. And whatever we are not considering when we are stopping at, let's say, in a degree polynomial, that is still maybe a significant, right? So that is the reason why we say that Taylor approximations are local, because they work well when we are trying to approximate around the point that we have chosen x naught, right? So
Correct.
for example, if we now plug this in formula into e to the power x, we get a nice form, right? And why is that? Because remember, the derivative of e to the power x is also just x. Sorry, e to the power x. So if we look at what's the approximation of e to the power x around x equal to 0 at the in the next slide, then we observe that this is what we get, right? How do we get this? So fx, so remember, we are approximating e to the power x around x equal to 0, right? So you had the first term as fx naught. So x naught is then f0. So e to the power 0 is 1. And e to the power x is the derivative for all the higher order terms also, right? So that e to the power 0 becomes 1. So that's why you end up getting this very nice looking expression. So how did we get that e to the power x is approximately the same as 1, e to the power r is same as 1 plus r. So this is the linear approximation, right? So we are stopping at just the first term. And then the quadratic would be, you take the x square by 2 term and so on, right? So that this should be just be a recap of, well, depending on, I guess when Shorish did the course or mine, high school math or college math. But Shorish, what's the computational implication of all of this? Is there something more interesting to learn about algorithms from all of this?
Absolutely. Absolutely. For example, if I'm interested in estimating, say, e to the power any value, right? So I can use this Taylor series function or approximation in my advantage to calculate the e to the power x. Because remember that e is a irrational number. right? E is a irrational number. It's like it doesn't have a value, like it's keep continuing kind of thing. Similarly, square root is a irrational number. Irrational
Square
number
root of
to
2, you
the
mean, right?
power
Square root of
x,
4.
computing will be very difficult, right? But I want a best approximation. So, but on the right hand side, I do not have any irrational number. I do not have any irrational number. So I can use, so I am representing a irrational number to the power x with the all rational numbers. Maybe if all real numbers, some real numbers, I know the value of x exactly. So here is the nice algorithm that is being developed in a simple algorithm. It has three concepts. One is the recurrence. Another is the some stopping. Sometimes we have to stop, and some adaptive steps. So what we are doing, the function has two one argument or input. One is the x, the value for which I want to e to the power x. So for which x I want to estimate the value of e to the power x, right? So that x. And then tolerance, that how much error I am ready to accept. Generally, we keep like 0.00001, maybe after 5 decimal or 8 decimal or 10 decimal. It is completely user who has to define the tolerance, right? And then what we do, obviously, if you keep the tolerance very low, the algorithm will run for longer period. But if you keep the tolerance slightly, 3 decimal or 5 decimal, it will converge quickly. I mean, it will not run for long time. So first thing we start, it has three starting things. One is the total. Here this is what we finally, because why I need a total? Because remember that these are all sums, right? So each term we will calculate and then sum, and that total will give me the e to the power x. So I want to calculate the total of each term. Then term, I am starting with the value 1, but it can be, we can decide what would be the correct term. And actually, here I'm starting with the first term, effectively term equal to 1. And then n is the 1 because that is the first iteration we can think of. While absolute value of term is greater than the tolerance, what we are doing, we are saying that the term is term times the next x by n. Why it is so? Now, if you go back here, let us carefully analyze x square and x cube, x square by 2 factorial and x cube by 3 factorial. Now, suppose I already calculated x square by 2 factorial. If I just multiply x square by 2 factorial by x by 3, I will get the x cube by 3 factorial, right? Now, similarly, if I have already calculated x cube by 3 factorial. With that value, if I just multiply x by 4, I will get the x to the power 4 by 4 factorial. So this interesting pattern I'm going to use in my favor. So
Right.
whatever
So
the last term, you
this is
multiply
a
with
this is like
the
a recursive
expansion. This is
relation.
the recursive idea. That
Right.
previous term, you take the previous term, multiply it with the x by n. You will get the new term. And this is consistent from the 1 effectively 1, then x by, obviously n is 1, so x, then x by 2, that will give you x square by 2 factorial. Then you multiply it by x by 3, it will give you x cube by 3 factorial. So this is a recursive behavior that you are
And
getting.
I guess the reason why we do it is because it saves us the amount of computation in some
Correct.
sense, right? Rather than calculating x to the power n by n directly, we are using the information we already have, and
lot
then
of lot of
right,
computational power we are just wasting, right? So we have
right,
to do it in a most efficient. One of the principle of good computational technique is if you already estimated something, you should not estimate again.
right,
Now, if you go back to the previous one, already you have estimated x square by 2 factorial. you should not estimate again. All you do, just multiply by x by 3, the pattern, and you get the x cubed by 3 factorial. So with the least amount of effort, you should be able to do the next level computation, and you should not recompute anything. If you compute anything, you store it. And so I have computed a x square by 2. I stored it at term and multiplied with the x by 3. I get my x cubed by 3 factorial. So this is the idea. And once you calculate the term, you just add to the total. So again, if you go back, you have 1, you add the calculated x, add to the 1. Then you calculate x squared by 2, add to the 1 plus x. Then you calculated x cubed by 3 factorial, add to the total. So you keep doing that.
So
Until
I think I just noticed this interesting pattern. It's as if we are doing each of the approximations one by one, right? We started out with one,
exactly
then we get the linear approximation, then we get the quadratic
quadratic,
approximation. So
then
I
you
guess
go
the
to the
question is,
cube.
till what point should we keep on going, right? So I think
Correct.
that is what brings us to this stopping criteria and
That is
tolerance.
how long we will keep doing it. We cannot do it for infinite many
Right.
times, right? That is where you have to decide that when my term is no more, a particular term has no more contributing to the total, I should stop, right? I mean, if you see that after a time, so you take a x value, suppose you want to do it for e to the power 5. Once you cross 5, x value cross 5,
In
then
process five, right?
n crosses 5. The after fifth iteration, what happens? X by n becomes less than 1. X by n becomes less than 1, and as n keep increasing, x by the n becomes smaller and smaller and smaller and smaller, and after quite a few iteration, x by n will have no effect on the term, and that time term will become smaller than tolerance level. Now, if you set tolerance level at 0.001 and a new term is even smaller than that, so that means basically I'm saying that this new term is not going to affect my total in any way. So I will stop.
Right.
So that is the stopping
And
criteria.
the reason we have this absolute value is because this can be used for negative values of x as well.
Correct. That time you need to be careful, and that is why we are using the absolute term and not the just term.
Right. So the nice thing is it can be used for values of x less than 1 or more than 1. But probably there's a difference, right? In the sense that if it's like, remember this local approximation property. So this would probably work much better if you are taking a value close
Close to zero.
close to
Yes.
0. And although I think so the
It
difference
will work for
probably,
others also. Only thing
right.
is you have to run the algorithm longer.
Probably, I mean, you would not probably kind of like see it, but there's a way to kind of like track the number of
Correct.
computations that
When
was
we will
required to calculate. And
do
then,
the hands-on, we will show that for x equal to 0, it will converge in 1 or 2 state. But if at x equal to 5 or x equal to 10, it will take more longer steps to compute. So we have to compute a lot more.
right.
So 3 new ideas that come with this iterative algorithm. Obviously, one is the stopping criteria, when should we stop, and convergence, will the algorithm always stop, or is there a possibility that it will never stop? Okay, and the error, when we stop, we have an approximation. Remember that it will never be exact. The only thing what we can do is the remainder term that has to be small enough that we don't care anymore, basically, right?
Mhm.
Uh, or bounding the remaining error is the part of using algorithm's responsibility. Uh, Taylor's theorem basically provide that. So these are the slightly, if you go deeper, these things comes to a
Right.
great extent in the numerical analysis kind of courses. These are very important.
Right, right. So I think the point in this segment was, although we started out by talking about e to the power x, but I think the idea is to kind of link it to these important concepts in algorithms, right? But
Correct.
is there some final lesson to take away from this e to the power x story and algorithms?
Absolutely, absolutely. So, if, I mean, there are, I would say, first thing is when a function is hard to compute, uh, replace it with some polynomial expansion. You can use Taylor series expansion is one such expansion. There are other methods to expand the function and build from its derivatives, and then keep the eye on the remainder. So you basically, if you have a very complex function, what you do, you expand the function using polynomials, and you each term you keep estimating and keep an eye on the remainder, and then remainder, as long as remainder is very small, you can say that okay, this polynomial, my estimate from this polynomial is essentially the estimate of this function. So
Right,
this
right.
is the
Yeah.
idea
And
that
I think we'll find several applications later in the course, and
many,
we'll go
many
into more
functions.
details
Yeah.
when
Three is we pointed out here. If you
right,
see, Vikram, one is root finding, that yield to maturity computation. You have a bond, and what is the yield? If you want to compute, that is one immediate application. Another is if you want to estimate the duration or convexity of a bond. Typically, these are the risk measures. You need that. Another
right,
is the numerical solution for differential equations, which we
right.
will use lot when we will discuss about the option pricing the options.
Right, right. But I think we'll come to this in more detail at that point. So
Correct.
perhaps I think we can
Stop
stop here for
here
a bit here
and
so
come
that you
back to
can
the
think about
next,
it and then.
next section in few minutes.